Hey everyone, well this one should be kind of interesting. There's a little bit of an unusual thing here. What I have here is a very, very large, very heavy DC to DC power supply. This is slightly unusual because as you can see here, this is good for 5 volts at 80 amps, another output at 5 volts at 80 amps, and a third output that's 2 volts at 150 amps. So this is a 1.5 kilowatt power supply. The max RMS current of 20 amps. So this is really quite the behemoth. If you actually look at the end down here, you can see that here are your power outputs. And it doesn't have screw terminals, it has bolts. So these are your 150 amps and these two are 80 amps. And these are all floating, incidentally. So you can, one of the possible things we're going to do with this, or that I might do with this, is if I need 12 volts at 80 amps, you can string the two 5 volts and the 12 volt supplies in series and get 5 volts at 80 amps, which is pretty impressive. Make an arc welder or something, or you could probably put these in parallel and get 7 volts, you know, put these two in parallel in series with this one and get 7 volts at 150 amps. That's a lot of power. So you can probably see, if you look at the end, that it's kind of a modular thing. You have these 3 modular power supply units, and then you have this big section here, which if you look here you can see this is the power factor correction module. This has an output module A8, output module A8, and output module F2. I've looked inside this once before, not very in depth. I don't want to render it non-functional because it currently works, because you know, it could potentially be useful. It's also kind of unusual. But anyways, seems like a bit of an esoteric oddment, so let's have a look inside and see what it takes to do, you know, produce 150 amps, you know, using common PCBs. You know, there should be some interesting copper construction in here just to produce that much output current. Well, so first thing of note, insulating paper here, insulating paper here. Wow. So first of all, metal fan casing. Second, look at all those power devices. Then actually, look at that output rail. So this is quite interesting. Man, look at these big, heavy copper. So, I think these modules lift out. It looks like I just have to take out some of these screws, so let's do that. This has been unpowered for a couple days, so I'm fairly confident I can stick my fingers in it without too much in the way of serious bodily harm. Let's see, is there another screw at the other end? Interesting, also date code. October 14th, 1995. Alright. What is rattling out? Just some washers, I think. Okay. So, these do not appear to have the second connection. What is rattling? Oh, there's metal inserts. Alright. So, we can see we have big edge style connectors. Only some of these are populated. You can see it obviously looks like they have places for 4 modules, though one of the modules only takes up 2 of them. Though interestingly enough, this big heavy current module only connects in one place. So my guess would be that what happens is we come in, we're rectified to high voltage DC, a few hundred volts, something in that range. So you get a couple hundred volts DC out of here, and then it comes in and it runs to these boards as a high voltage DC. But I'm not entirely certain, because I know that the outputs of these are isolated. They're floating all relative to each other. So I wonder how it's really done inside. So is this? Actually, there's an interesting idea. I wonder if I could power this up on its own. This is a 24 volt, 0.25 amp power supply. That's a chunky sucker. So it appears that in here we have so these are supports for the what I think what should be called the two section ones. So the single section, or the single supported section, or the single wide power supply modules did not couple to these, but the double wide did couple to this one. So I bet you could put that in either these two or these two, but I guess they don't want you spreading it across the middle. You can also see we have all through-hole components. It's also double-sided board, but they've also got some wire jumpers in there, though they're very nice wire jumpers. This is a cable running somewhere. Lots of parts. You can also see, look at that big high current bus. I'm actually tempted. See, so if we look at one of these, we can see we have big plane, and then you can also see that there are vias there, so it only has these two power inputs. Also, there's, you know, kind of a little look at it. We'll get into it deeper at some point. You can see where the power transistors are. Big. Wow. Man, that's got gate drive transistors, or gate drive transformers, I mean. Interesting sucker. I wonder what all of these input devices are for. Well, I'll get here in a minute. What I want to do is, I think I can probably power this up without anything in it. We'll see what it does. This is probably not the greatest idea. I also don't think I'm going to take that much further apart because I don't see how it comes out. I think this whole thing comes out as a unit. Well, you know what, I'm going to do that. So let's look at the power factor correction stuff first, I bet. Here's another date, October 30th, 1995. So this plate was added by a user because you can see it mounts this little switch, but the actual power connections are under there. Because they're assholes, these are not. Oh wow. Look at these screw mounts. So it appears this screw goes through a piece of plastic which then holds the board. Oh wait, no. So what happens is, so these screw holes are they're like half moon screw holes. So this piece of plastic serves as like a clamping. Yeah. See, so this plastic has half of it cut away and the screw hole has half of it cut away. That's bizarre. I guess they couldn't fit screw holes on the circuit board and they didn't want to make the board any bigger because they're cheap as hell. Wow, that's a cost-cutting measure. So, how is this? I'm not sure if it's multi-layer, but you can see here's the power takeoff with these kind of redonkulous bus bar things. And they've got these cute little bits of fabric on them for insulation. That's so adorable. And it looks like this is like high current strapping from one side, from this panel to that panel. You can also make out some of these really big copper areas in here. Alright, so a few connections. There's this screw I dropped in there somewhere. Oh, there it is. Long nose pliers for the win. So, here we are. So we can see that this is just kind of, I'm going to go with the word I used last time, which was redonkulous. Just because the amount of hand assembly in this shit is just nuts. Incidentally, I think I need to mark this too. Well, first of all, this silicone glob appears to cover a little whoopsie-doo. There's a cap under there. It's hard to make out. But if we look on this side, we can start to kind of see, you know, lots of stuff. I mean, here's some interesting, oops. I mean, all sorts of interesting bits. So, I mean, you've got a whole pile of interesting little transformers. Look at that. It's got 2 windings through the primary and a big secondary winding, and there's a little spacer on it. Yeah. And over here we have another probably hand-wound custom transformer held onto the board with some silicone. Look at some of these exotic inductors. And then we have this big heatsink. Here's a TR220 standing up, but it's glued to the capacitor. Silicon-wise, nothing too adventurous that I've seen. We have 74HC123. I think that's a one-shot. 74HC73. Here's a 319. LM319, I mean. LM339, comparator 358, LM358, LM393. Sorry, this isn't LM393, not a 358. Here's another, oops, here's another, this is a capacitor. Yeah, it looks like that's what all these are. So you can see there's a cap here, and they solder it on and then they cover it with silicone, presumably to hold it in place. This is an interesting part here. This is an ML4812CP. Over here we have an MC34152, MC34152. I think those are op amps. Number of transistors. Down here we have some Ixis parts. DSEI 12-06A G9521. I think 95 means 1995, week 21. It's probably a production date. Another thing you can notice is that all of these are using ceramic insulation washers. I saw that on the other side as well. That's kind of interesting. I haven't really seen those much often before. So anyways, this board looks to be basically the logic for the whole thing. Over here we have really big stonking chokes. So 4 of them too. You know, this is very heavy wire. This is kind of a weird apparatus. So signal wire comes into here. This wire goes into this other connector, which joins the board somewhere else. So I guess they're using this as a combination jumper from places on the board as some other stuff. We've got a couple more big power devices down here. Some big wires. That's heavy. That's like 14 gauge or 12 gauge. And then there's more. Okay, so those 2 are diodes. And I can't make out what this is. I'll look closer in a second. But you can see that down there we have all of the bypass capacitance and 4 enormous capacitors. 1, 2, 3, and then 4 here. And then there's some interesting stuff here. Look at this interesting transformer. I wonder what some of that is. Wow, it's a very just interesting transformer. Custom magnetics in any event. So, and then here's our fuse, which I don't know how you're supposed to replace. But it's a 25 amp fuse. I guess you could kind of pull this back and stick a screwdriver in there and pop it out, but it seems ugly. Here's our line input. You can see protection, you know, C204. These are probably 0.1 mic caps across some of these inductors or something, I don't know. Here's a ginormous film cap, and I bet these are inductors or chokes or part of the power factor correction. Oh, that's also interesting. If you look at this board, you can see that they've notched out the silkscreen for pins. But looking at these slots, there's no pins on that side, so I don't know why this is. You know, this is just going against a flat piece of plastic. I also don't see much going on with the pins on the other side, though. This board has this interesting matte silk screen, which is much harder to see through. You can see look at these inductors. They've got these widely spaced, that's interesting. So these are quad filar wound, which basically means it's wound with 4 individual strands. I don't know necessarily. So they're wound with 4 strands, but the strands are tied together at each end. I don't know if that's necessarily the permutation. I know bifilar is used when you have 2 windings that are basically wound together but are used for different connections. But anyways, these look like they're also current shunts of some sort. You got 4 turns and then you have 1 turn, which may be used for the actual sensing, and it's just all on a ferrite. And then your power output is done through these press-in bushings. And then the whole heatsink clamps together through those 3 holes. And then this, I don't know, I don't think there's that much airflow here because it's not directly in line with the fan. Anyways, so that's quite interesting. There's not as much in there as I expected. So let's kind of plop this back together. I fail at connector. So I think I've got it back together. Some of the cables were really cranky. I don't know if they were formed a special way or if they're just difficult. Fiber shroud fell right off, so marking that was clever. Okay, so anyways, over here, these are all IRFP 450s. Down here we have, actually I'm not familiar with that semiconductor logo, though they're marked S6065K. And then these 2 devices over here are FEP16JT dual diodes. So they're marked a little diode icon. So on the back plane, we have, these are 7815 and the 7805, just bog standard regulators. Nothing creative there. These are transistors, they're marked ECB. Here's it, 14070. So down there's an LM393, excuse me. And then that is interesting. That is a UC3844 in a socket, which I guess means they may see somebody needing to change it. More transistors. What is this? MPS 2222. It's a standard 2222. That's kind of amusing. Anyways, so that is that. Let me put a couple of these screws back in here and then we'll move on to the other section. Actually, what I want to do now is see if it still works. Well, or at least the part that I have here. Otherwise I may have put these 2 big straps backwards. So drip off. Puts out 24 volts, enough to run the fan. Actually, if it's doing that, that was interesting. You hear that boom, and the lights dim. Yep. 310 volts DC, 330 volts DC. So this looks like basically doubled 120 volts. So it's the RMS doubled 120 volts or 115. So that means that probably they switch between doubling in 120 and straight up rectifying in 240. Man, that fan was a lot of air. Also, look at how long the capacitors in there last. Big ass ballsy motherfucker. So they bounce between straight up rectification and voltage doubling so that they can easily switch from 110 to 240 without too much trouble. That's a very common technique in switch mode power supplies. Because that way all the circuitry is just designed for, you know, basically 300 something volt DC input. So the other critical thing is that that was also, you know, it being 330 volts means that it's not mains isolated. So whatever is resulting in the, you know, the outputs being isolated from the mains has to be done in the subboards, which we will see in a second. This is being a difficult screw. Alright, and then I bet these are also like power good signals. There's just 3 logic signals there. So, on to the more interesting things. Let's leave the big one for the now. So what we have here is... Okay, I see how this works already. So here's it looks like our main transformer, I think. Really? So our power comes in here, you can see here. What we have here is a fuse that is 6.3 amps at 50 volts. So these two are our 330 volt DC input, runs into the fuse, and then what we have here are 4 big 12NA50, but they're marked GDS, so these are FETs. And it looks like the output from this FET, yeah, okay, so the outputs of these FETs appear to run into this winding here, which goes into the top of this transformer. So this transformer must be good for 5 volts at 80 amps. That's 500 watts or so. Oh no, it's 400 something watts. I can't do the math in my head because I'm sleepy. Yeah, that's a lot of power for just a little dinky transformer. I mean, it's 400 watts. It's 400 watts right on the nose. Derp. Yeah, so that's a 400 watt transformer. That seems kind of surprising. Well, I guess I've seen computer transformers that are similar. And one thing of interest that you might note here is you see these 2 devices here, and what these are is these are gate drive transformers. So basically that gives you, this is your isolation gap rather than using optos. They have everything on the secondary side, and then they just backdrive the main transformers through gate drive isolators. Also interesting is if you look down here, that red-orange blob, this thing, has a lead going through it, and that is a current transformer. So that, let's see. So if we look at those white leads, both terminate, where is it? So both of them run under here to these 2 solder points there. So it looks like the current from here runs up this leg into the transformer back down to that pin there, which is then jumpered across to here, and then it runs through the gate drive transformer. But I don't see where the high current return from this other wire is going, because the trace connected to this is just that narrow piddly trace there. Which then runs back up to this point up here, which then goes through. Now it's kind of interesting. So yeah, anyways, you can see, so you've got your main switching transformer. This, I don't know what the hell that is. Let's take off this little controller board and have a look at what's underneath. That seems to be screwed into plastic. So is that a ribbon cable? No, it's a socket, but it's goddamn. So they taped this in place. Guess that's one way to prevent it from vibrating loose. Sticky tape. Solving all of the world's problems. One failure at a time. And why do they even feel the need to tape this? Wow, look at that. These are really nice machine-tooled sockets, too. This is top-quality stuff. Look, it's machine-tooled. So, here is our output. And it appears these have to be diodes of some sort. So it looks like this is a yeah, because you look at how they're all strapped together. That's kind of strange. So obviously there's a big copper port here and there's another copper port on the other side. And it looks like this is the center tap, and then these are probably driven opposingly. So only one half of the winding is being used at any one time. But man, look at the size of those contacts. And then they felt the need to actually, this is just copper braid a couple places, and then this goes into that pin there, which goes into that pin there, which goes into that pin there, which goes into that pin there. Oh, no shit. So this is a choke. This is a 4-turn choke. That's weird. Yeah, so you can see the current, you know, basically the center tap comes into here, jumpers over to this lead, comes into here, jumpers over to this lead, comes in here, jumpers over to this lead, comes here, jumpers over to this lead, comes here, runs over to there. And then it looks like from this lead here, which is the last turn, it then runs over to the output, which happens right here. Yeah, so that's interesting. Look at that. They're using the PCB as part of the layout in this big kind of PCB-based choke, where they've got 4 turns on here. And then, so if you look down here, there's this one continuous plane here, which is going to probably be one of the rails. Actually, that big contiguous plane is going to be negative, because we can see that this here has to be positive because that pin goes to the positive of these capacitors. And then I guess all these are is diodes. So I wonder why the diodes are so much more heat sinked than the actual switching FETs. I think these would produce more heat. You know, if these are if these are Schottky or something, it'd be relatively low power. You can also see, look at the via stitching down in there, just to get all that current through the board. They've left the solder mask off and all sorts of fun stuff. That's a pretty wild little board. You can see they've got these interesting little standoffs. Oh! So that's interesting. So if you notice these standoffs, I thought this was like a plastic spacer, but these are actually both ferrite rings. So they've got ferrite rings across each of the output connections. There's a brass post, and they're just like, hey, we can plug a ferrite ring over that. There's a little bit of silicone holding them down, and then the output straps come through these 2 screws. And then if you look down there, there's actually a little PC board there, which looks to have even more capacitors across it. What are these capacitors anyways? 2700 mic at 6.3 volts per cap. We've got a few transistors down here. MPS 2907, MPS 2222. So it looks like these are all just Well, hang on, this is a U. 431. So this is an S431, and that's just a programmable voltage reference. That's probably one of like the voltage reference for this whole thing. And then there's a few pots over here, which you can just tweak through the output, and I bet those adjust the output voltage to some extent. But yeah, this is just an output choke. That's a really wild construction. I haven't seen something like that before. I kind of want to take the transformer apart just to see how it's wound, because you can see just these. It's a flat blade of copper for the output windings. It's rather unusual. I'm just still surprised they can get enough current through. I mean, I guess they do. These aren't switching. I guess it makes sense that this would get hotter because there's a lot more current here, and 0.3 volts drop at 40 amps, because each of these are going to be carrying. Each set is going to be carrying half. There's going to be a lot more power than maybe 0.3 volts at half an amp or an amp. These have to switch about an amp, because it's 400 watts output and it's 330 volts, so they're switching like an amp and a half. So I guess assuming they switch fast enough, which they should with these gate drive transformers, assuming they're being driven properly. Incidentally, yeah, so these transistors here appear to be driving the gate drive transformer, so these are probably a pair, like an NPN and a PNP. And then there's just a bunch of control logic here, which probably just does... Actually, this whole connection here is entirely unused in my power supply. It only uses these three. I wonder what this is. Anyway, so this is kind of a herkaderp. So I tried to unscrew this, and I unscrewed the standoff from the base rather than unscrewing the screw from the standoff. So this standoff goes here. That screw, the screw it's going onto appears to actually be screwed into the... Sorry, that's not a screw. So they're actually using... Okay, that's amusing. So it looks like they press this screw in, or whatever it is, probably a PCB end mount screw, and then they just soldered over it, and they're actually using the metal of this screw to help stitch the vias together with much better, with lower resistance. So they're using the screw as like the via from hell. Cool, all back together. And then just to save myself an effort, if we just compare these two, you can see they're completely identical. So I'm not going to even bother with this one, because this is the exact same as that one. It's even the same. 60942, 60942, 101D, 101D, yeah, BD 60940. So I'm not going to bother with this one because it's identical to the one I've already looked at. Oh. I did forget to put this sheet back in the main power supply system, didn't I? Let's put it there for the time being. So this should be significantly more interesting. So I suspect we're going to see a very similar architecture where this is our rectification and these are our switchers. Though, actually, where are the devices on there? Oh, they're mounted on the sides. They're mounted there. Yeah, so these power devices are 1N12A50. Really? They're the same FETs. Yeah. W12NA50. W12NA50. Yeah, I guess if they overspec them for one, they can just use them on the other. Without too much trouble. And okay, yeah, these are diodes indeed, I can see that. Let's see, how can I get the cover off of this thing? So another thing you can see is this is clearly your output bus. And these are actually all electrolytic bypass caps, each one of these little spots. And then I think that, yeah, they're using copper bus bars. Actually, let me... Put 300 volts DC. Yeah, so this does, they are... Look here, we have output 2 volts, 150 amps, input 300 volts, 550 watts. So surprisingly enough, this is about the same, or it's not significantly more wattage than the other one, than the 5-volt version, but it's significantly more current. So that looks like that's just a mechanical support for this. I guess they, oh yeah, so that makes sense. So this is your output, and you want to make sure the current flows past all the caps, so they have it isolated here, and then they only junction it there. That lead. So this lead goes to another current shunt, whereas it looks like these two leads are the actual input to the transformer. Shazam. Wow! We'll have a closer look at that in a second, because that's going to be interesting. So here is our output, and wow, look at that cap setup. Ken has caps. So we have, that's interesting, these are 10-volt caps. Why would they go for a 10-volt cap in a 2-volt output? The 5-volt one only has 6.3-volt caps. I wonder how far up I can adjust this. But yeah, you see this giant metal plate here? That's my output. It's actually interesting. Look at this. They've got a notch here intentionally to make the, you know, to kind of, I guess they want the current to run closer to the bottom edge, I guess. Because that means you're not going to, you know, most of your current's going to flow down there, not much of it's going to come up here. That's interesting. So this controller is exactly identical to the other one. So it looks like they share as many parts between the two as they can. That's quite nice design. The goddamn standoff came loose first again. Let's see if I can not bend the pins this time. Success. So there's hardly anything under there. We've just got a couple caps, adjustment pots, and gate drive transistors. And these are extremely low resistance resistors too. That is brown, black, or blue, black, gold. That is 6.6 ohms. Or 6 ohms, I think. Yeah, it's 6 ohms because it's 0.2. Yeah, blue, black, gold, and we have yellow, purple, gold, which is going to be 4.7 ohms. And then you can see the windings for these run over here. See here we have winding A, so the sign. You can see here's our current transistor, you know, our current shunt for measuring the primary current. Little cute little loop goes through there. So you can see the current comes. It looks like it actually uses this jumper here, really. Yeah. I guess that's a heavy jumper. So the primary current flows through here. Well, it's only 2 amps. Runs to this node, goes through here, comes back up to the bottom side of the screw terminal through this winding here, and then it goes into the transformer. Also, it looks like this is just, I could probably reverse these two connections without any harm because they're just reversing the primary. That wouldn't have any particularly significant effect. Look at how far up that cap is stood off the board. I wonder if that's intentional. Well, I doubt it, because look at this one. It's probably a minor manufacturing defect. Didn't hurt anything. Gate drive transformers. Here are these big, really nice stacked headers. Almost looks like they have multiple headers stacked up, but they don't come apart. So over here we can see, look at that. So they've got these mounted vertically, and then they've got a metal post that's either pressed into the circuit board or soldered into the circuit board, and the resistor leads are folded over and stuck in there. That's got to be put together by hand, I bet. So that is, your power comes in, runs to the central node, and then these, so it kind of makes me think current, well, oh, nope, this is a, it's a snubber, because you've got this cap going into these resistors going into the central node. So I bet this is the negative, yeah, because the other it's positive fuse. So, and then I bet these two connections here go to the yeah, they do. Okay, so yeah, because one goes here and the other lead from the transformer runs, yeah, right to there. Okay, so this is just these are big resistors in parallel to give you more heat dissipation, and then you have a capacitor. Yeah, so these are just a plain old-fashioned, RC primary side snubber to dampen transformer, oscillation. That's a very common way of doing it. Also interesting, you can see here we've got these are marked CR, so these are diodes, also 2 pins, so it has to be a rectifier. But if you look at this, they've got a little plastic thing stuck through it. And the reason they're doing that, I think, is if you look down here, you can see that it sits there, and that prevents this from flexing to the point where it would contact the heatsinks, because it looks like the heatsinks are not isolated from the FETs. Yeah, so you can see here is our negative rail, which appears to run to, entirely certain, it runs to this FET. So they have to be driving this they're driving it H-bridge style, I'm fairly confident, because if you were doing push-pull, you'd only have 2. Or, I guess you could parallel FETs in push-pull, but it seems kind of wacko. Well, not wacko, but the layout doesn't suggest that. Anyway, so, because here's your high voltage. Oh, there's a whole pile of jumpers under there that I can't make out. Some more diodes. And I'm not going to be able to totally figure out what's going on here just because there's a whole lot of jumpers running this way that are hidden by the heatsinks, and I don't want to take the heatsinks out. But anyways, yeah, so you can see there's not much going on over here. Obviously, these are the 2 gate drive primaries. It's interesting. So they're joining traces at right angles with other traces. I do that occasionally. I'd generally like to avoid it. I'd put like a little copper circle there to reduce this angle so you only have 45-degree joints, but it's kind of nice to see somebody else other than me doing it. Because I always feel kind of guilty when I do that. I feel like I should run into a pad or something. That's interesting. So these capacitors, this cap and this cap here, are in series with the gate drives. So I think what's going on here is that these are probably so I think the reason this is 4.7 and 6 ohms for these resistors is probably because these are not these transistors are not perfectly matched, so that basically the turn on and turn off time would vary because the one can pull up harder and the other one can pull down, or vice versa. So I bet they use different value resistors to match them to control the slew rate of this output very precisely, so that the turn on and turn off is synchronized. Another thing you can see is it goes through these 2 resistors, and then it goes through these 2 caps here. So these caps are actually in series with the gate drive. So that actually means that, basically with a single, a half bridge driving, it pulls high, it turns the FETs on hard, and then the cap starts to charge, through the transformer, and then if you switch it the other way fast enough, it'll discharge. And basically what happens is that, the cap kind of winds up, one end of the cap winds up sitting at about half of the voltage, half your supply rails, because it keeps bouncing up and down, so that you can basically drive the FET gates very strongly positive or very strongly negative. It's a cute way of doing it. It's very nicely designed. But yeah, and then there's just the little insulating washer. So let me put this back together, and then we'll move on to the final part, which is probably one of the more interesting parts too, which is that giant high current transformer. Because I can already see diode snubbers on there. I'm stringing you along! But wait, there's more! So this is the same type of screw assembly here, though they're not using this to carry any current. So I wonder if they've abstracted enough of the components that control the behavior of this little controller board to the point where they can use the exact same controller board with all the same parts in multiple devices. Like, I wonder if a lot of the passives that you saw down there form the things that affect, the feedback loop of this little controller board. Because that would be quite clever if they could have like a general purpose controller board that handled, all of whatever their shutdown logic is and so forth, and then, all of the passives that control the slew rate and so forth were external to it. So this has a few devices on it. We have a 7474, which I think is a flip-flop. We have a UC3846, which I believe is a switch mode power supply controller. There is a LM339, which is a quad comparator, IARC. And the last thing over here is a LM358, which I don't remember what it is at all. There's a few little transistors. And PSA 2222, PSA 2907. So I think they're using 2222 and 2907, which is probably the PNP complement, or close to the PNP complement of it. So another thing you can also see is there's, much like the other one, they have a circuit board mounted up vertically with more parts on it. And that actually necessitated 2 different size capacitors in here. It's quite the assembly. And then this is actually one of the output terminals. So here is quite the interesting little bit. So this is our transformer. So you can see a few things here. You can see that this internal white section is going to be your primary. And then let me see how this is laid out. Obviously this black winding here is your secondary. And it appears I'm not entirely certain how they're bridge rectifying. I don't think they could be. I think this has to be a half-wave center tap. Unless these diodes, they can get these in 2 different polarities. I can't see any of the writing on the big diodes. So basically the big deal is that I can see that it appears... Well, actually, I'm not entirely certain what's strapped where. But here's, you can see that this is obviously like the output inductor. It's a choke output power supply, I guess, of some sort. But you can see this. Look at the size of this wire. I guess that's capable of carrying 150 amps. It's kind of surprising. So I guess that this is pre-regulation. So if they're losing, so they have some R losses in this cable, the regulation of the system should take it out. So I think this may have 4 secondary windings. Because I think what happens is, so this copper wire runs into the sleeve here, which then has, it looks like 4 of the black wires exiting it, I think. I don't actually see where the 3rd one goes. So this wire comes, wait, no, there's another, oh, okay, hang on, I'm stupid. Yeah, so this does have, so this is actually wound with 2 leads. So you can see that's what I was missing. So that you have 1 turn through here, another turn, and then 1 comes over here and 1 comes over here. And it looks like it exits. Each of these has 3 leads coming out of it. I can't really follow the secondary windings, but I think that this has 2 half-wave center tapped outputs, maybe, and it looks like they're wound. They're wound in mixed directions, so that for every wave you're always getting some sort of output. It's very strange. So that. Up like that and then runs in there. So it's either that goes down like that and runs there. So it looks like there's actually only 1 secondary winding, Because it's, I mean, this lead here, for instance, runs over to here, around, and then terminates into this sock, I think. But another thing you can notice is that we have big power resistor. This is brown, black, black, silver. Gold. You know, so that's, you know, and then there's also a big ceramic cap, and then there's something in this heat shrink tubing over the, and that's across here, and I think that's to absorb the diode turnoff, you know, basically for diode turnoff snubbing. I'm not entirely certain. This is all well above any power rating I've ever done any work at. But, it's quite the apparatus. And you can see the damn it, I wish I could make out the part number on any one of these diodes. This is 9530, so I bet it's a 1N9530, but I'm just guessing. But yeah, I mean, this is like heavy metal, man. I mean, even the primary is pretty chunky. That's only carrying 2 amps. And those poke through that hole. Serious business. But yeah, so this is definitely isolated too, which is what I was curious about. Here's another thing that is kind of off topic, but I thought was kind of interesting. If you look at all the standoffs in here, the standoffs are like, they're mechanically retained, but they're like free to wobble, which I guess allows case variance. I haven't seen something like that before. It's kind of unusual. Fuse is factory replace only. Let's see, I didn't forget anything. Good, the secondary is broken out properly. Seems like a lot of these connections, like the connections here, are kind of overkill considering the reasonable expectation for primary current is only maybe 2 to 3 amps. You know, why bother with this giant screw when you're going to run it through a trace that's only that thick? But, yeah. It might be for mechanical reasons predominantly. Anyways, you just kind of adjust that so it's lined up. Put my head in the way. You just don't care. At least now I can shake the screws I drop in there out. Well, that worked well. Yeah, I don't think you can power this on without the lid, because the lid is what maintains proper spacing. Fortunately, I won't be too crushed if this doesn't go back together. Slightly miffed, yes. Crushed, no. Making an angry hissing noise. 2 volts, 4.7, 5. So does it need to be adjusted a little bit? Yeah. Actually. That's easy enough. Oh, that angry hissing noise is coming from the 2-volt power supply because the pitch changed. Man, that fire runs for a long time. Alright, well there you go. So there's a really monstrous power supply in its internals. Hope you enjoyed it.